Okay, now I have drawn this circuit already before, and one thing you should keep in mind is that the LTSPICE does not has the model of LM741. So what you can do is that you can go to the Google and easily download this LTSPICE model by just writing the LM741 operation amplifier and LTSPICE model, and the quickest link will come to the screen is ti.com. Okay, now when you click it up, then in the next tab you will see that it will be offering you the data sheet and the description of this product, and if you scroll down there will be a model in this .mod extension. You can easily click on it to download, and wherever the file gets downloaded, just move to that section. Okay, the file will be appear over here in the .mod extension, and you can open it up by using the LTSPICE, but that is not necessary. So what you need to do is that you need to go into the LTSPICE software and move to the component section by pressing the F2. Just write operational amplifier and get the generic block. Okay, the op-amp2. With the name of op-amp2, it can be easily extracted. You can place it somewhere wherever you want. Now when you right click up, there will be two things be appearing over here. One is the spice model and other one is the value. Okay, so now you need to provide the two things over here. One will be the spice model and other one will be the value. Okay. Alright, now in order to check this present the specific model of this LM741, you need to include the directory over here. So you can easily do that by first of all clicking on this .op, and a window will pop up in front of you. Make sure that there is a spice directive that is been checked. So you need to write .include and mention the address where that file is located. Okay, so how you can do that? It's very easy. Just move to the file location and right click on it, move to the property section, and here is the address. C, it's in the C, the user. You just need to copy it up and place it into the .op. Once again, .include space and paste it up over here. And don't forget to mention .mod, which is the extension of this file, and press OK, and wherever you want to place it up, just click over there. So since I am being using this model one and I have already pasted my code over here, so I can remove it for the sake. But the second thing, you need to find the value of this op-amp2. Since it is a generic model, you cannot use it for your purpose. So you need to know what is the model of this what is the value of this operation amplifier which you want to specify. So it's very easy. Once again, you need to go to that file and open it with the LTSPICE. This is this over here. Now when you do, the file will be open in the LTSPICE software, and here is the .sub circuit, that is .sub CKT. This is the model which is LM741/NS. You need to copy it up and move to that component and place it over here, the value over here. Okay, I'll press OK, and this is almost complete. Okay, now this is my the complete schematic diagram of my differential amplifier, in which I am giving the input of a noise signal that is having the 2 millivolt 50 hertz, and the inputs are being common, and the resistor are 1k and 10k, and the output is at 100 ohms. Okay, for the biasing purpose I have connected the configuration just like this one. The V3 and V4 are the batteries. V is the positive, that is connecting the positive terminal of U1, and this one is the negative, that is being connected with the LM741, the negative terminal, with this. So this makes my circuit to be complete. So I'm assuming that CMRR for this 741 is actually 90 dB. However, typically it's 95. Okay, so our based upon this assumption, our output might be a little bit different from that we have proposed in our calculation. Okay, so don't worry about it, just you need to simulate it according to the given conditions. This is the V1, this was the noise, I assume that was 5 millivolt. Since I have connected both of them to be common, so I'm using the V2 and with the 50 hertz for both of my inputs. Okay, so when I just press the run button, it's asked me for the transient analysis. Let's say it's a 50 millisecond, and just delete the previous curves, and let's check it out for the new one. Okay, this one is a V2 and this one is a V1. Since both are same, there is no difference. And this one is my let's first of all make another plot over here, and also change this position as well. Okay, this one is my input, and let's plot the output over here. So you can easily see that the output is also having the same frequency that as compared to that of the input voltage. And let's see, that's the signal is varying from approximately 11.439 millivolts to somewhere less than 11.4378 millivolts. So you can easily find out the difference by calling the cursors, and just find out the difference over here. And according to our given conditions and circuit, the output is 1.285 microvolt. Okay, now that means that first of all, that our input noise has been suppressed at the output to about 1.28 microvolt, although it is higher than that we have calculated based upon this the gain of this amplifier and our assumed CMRR, that is 90 dB. Might be it is the circuit is assuming to be less, so we have just used the typical assumption for the circuit. So if you that means that our assumed 90 dB is much higher. So that also suggests that in the current situation, the value of the CMRR is actually near to 80 dB. It's assuming to that, so that will make it to help us to trace the output to be nearly 1.2, so that can vary between. So there is no problem in that assumption. You just need to understand the concept that how the input signal is being suppressed at the output by using the differential mod of the amplifier. So I do hope that you have understood the concept of differential amplifier and the impact of CMRR in the transient phase. Now just remove all these extra phases and let's check the what is the impact of changing the frequency and over the output. How does our differential amplifier behaves in terms of the gain when the frequency is increased? So before that, I have told you that the ideally, as the frequency will increase, the gain of CMRR will be reduced. That means that the ability to suppress the noise at the input will be gradually decreased by increasing the frequency. So let's see in this using this LTSPICE simulator. Okay, now you can do the simulation of AC analysis by just going to the edit simulation command and set the values to the linear, number of points 100, start frequency 1, stop frequency 100 megahertz, and just press OK and click the run button. And when you do that, you can easily click at the output and it will appear like this. You can check for this, everything is fine. Okay, so this one is the output response. Just delete the phase for this point and okay, now you can easily see that you can easily find the bandwidth by moving one cursor at the maximum point. It's 80 dB, and call the second one and find the lower frequency. It should be at the 3 dB 3 dB difference. So here at this point it is 2.95. so let's move a little bit. So it's fine. Okay, now just note down these minimum frequency, that is 719 kilohertz. Similarly, you can do that by moving the first cursor at the same location. Okay, now you can find out that the difference of these two frequencies shows that the bandwidth of this system amplifier is 2 megahertz. Okay, that means that you can allow the frequencies at maximum 2 megahertz frequency that can easily pass through it, and after that, by increasing the frequency once again, the gain will start to decrease. So that was all about the today's session. So I hope that you have clearly understood the whole functionality of this differential amplifier, and if you have any confusion, just mark it in the comment section and I will get you back.